Okay. Okay. So far, okay. Okay. Oh, exactly 10. Okay. The problem is these clocks.
Yeah, these clocks. Even though they have security, but they will clock. They will match the time.
We can manage it.
I remember they were like 6 minutes. Okay. 6 minutes.
It's 9:57.
Yeah, even 8 minutes.
Careful.
Yeah.
58 now. Okay, that's
Do you have a summer or winter time when you change the clocks? We don't. In America, we do it.
Luckily, we have only one time zone.
Right.
That to Calcutta.
But
We call it as
tell me,
Asia time.
why is there so strange difference of, like, between Houston at 11.5 hours? Why you get half? Why is half not into the number with the rest of the world? You know what I mean?
Tough. Because maybe the curvature and
So they said it's the most optimal to cover the whole country.
well, some cases it is 2 hours 35 minutes.
Yeah. But so, for example, with all other countries, essentially,
Situation, the globe sector itself.
so with the
If
France,
you're here,
1.5. Yeah.
Yeah.
Houston, 11.
But here in the big country, only one time zone.
Yeah. China also has one time. Too crazy.
But I think US have 2 or 3.
No, US has 3. Russia has 9.
9.
Yeah. So,
Near you. One guardian? Huh? Content?
yes.
don't want. You can start. You can start? Okay. So, morning everyone, welcome. Thank you for staying alive. We still have 10 more lectures. So we will continue to discuss stochasticity and randomness. We will talk a little bit more microscopic origin of randomness, some more mathematical tools today. Again, I remind you, interrupt me, ask me something. As you can see, we have different background. I have a lot of chemistry, too much, I guess. Feel free to ask. If you don't understand, just scream. Okay, so to remind you, there is the plan, right? Remember, so we at the beginning we discussed already this chemical kinetics last time, and we argued about chemical kinetics, catalysis, and molecular rate laws. We try to discuss to show where this randomness, stochasticity comes and how to understand it. Today we go to the second part of this plan. We will discuss a little bit, very little theoretical tools of how you can deal with understanding the effect of stochasticity. Yeah. So and the lectures will be later. All of them will be examples of different systems where we will learn by examples. Okay. So one of the main tools for understanding randomness and stochasticity is master equation. Sometimes it's called chemical master equation, but it's essentially the same thing. So it's important for analyzing dynamics, and this is the things which reflect the balance of probability. It's closely related to chemical kinetic things, as you will see in them soon. But it's just a balance, it's conservation of probability. And just a simple analogy is, in a family, right? You're giving money from a salary or whatever you do, and then you're spending money to vacation, cars, education, whatever, right? Overall, there is a balance. The balance of coming money, the balance of leaving money. Master equation is exactly the same. Master equation deals with the balance of probability. Now, why master equations is important for us? That's because, as you probably know, there are equilibrium phenomena, equilibrium processes, and for equilibrium processes there is a science called thermodynamics. And it can describe the system. because it's a well-developed theoretical framework. It's a fundamental, one of the fundamental things. There are two fundamental sciences: quantum mechanics and statistical mechanics, thermodynamics. So there is a well-developed framework, which probably many of you did. There are two postulates, two laws of thermodynamics. So in other words, there's well-developed mathematics for equilibrium processes. We don't need essentially master equations for the system. The problem comes in non-equilibrium systems. I mean, the majority of systems is non-equilibrium. All biological systems are non-equilibrium because in biology equilibrium is death. We don't consider death. Okay, all biological system is non-equilibrium, and the majority of chemical systems also non-equilibrium. But in non-equilibrium systems, there is no framework analogous to thermodynamics. There is none. So essentially the only quantitative approach for systems. So master equation. So we will try to derive this master equation in a very simple way. So as I said, I'm still trying to have very little mathematics. Very simple way you will understand, especially. So let's say the probability of transition per unit time is from here to here is u. Probability of transition per unit time, it's rate. So chemists would call it rate, transition rate. But it's the probability of transition per unit time. From 1 to 2 is u. Probability of transition from say 2 to 1 per unit time is w. So to describe the system, we can assign probability form. So this is T1t, the probability to find the system in state 1 at time t. T2t, probability to find the system at time t in state 2. Okay, that's all we need to know. But how to find them? Well, to find them is relatively easy. So let me ask the following questions. What will be the probability to find the system at some time t plus dt? Okay, so at t plus dt. I want to know what will be the probability to find the system at time which is t plus small additional time dt. I can answer this question. That's because this is probability to be found in state 1 at time t and having no transitions 1, 2 in this time interval, right? You understand, right? So if I want to know what will happen in this given state, so let's say, what if I want to know what will happen in this room tomorrow, right? There are two possibilities. Or we all stay here until tomorrow, right? And we know we will be there. Or some other group of people we will leave this room, but some other group of people will come. So in this language, plus probability to be found in state 2 at time t and transitioning in the time interval delta t. Clear, right? Very simple argument. Good. So if this is the case, I can write it mathematically this way. So this is the probability to find the system in state 1 in time t plus dt. It's time probability to be in time t in 1 and having no transitions. This is, remember, u is a probability per unit time. So multiplying by dt, you will have a probability. Or if you start here, and this is the probability of transitioning w dt from here. Dt is very, very small. Okay, so if this is, look at this equation, then what you do, obviously, is obvious things. You do Taylor expansion, right? dt is a very small parameter. If you tell Taylor expansion, you will get this equation. That's a derivation of master equation in a simple possible way. Again, it comes from the balance of probabilities, right? From the balance of probabilities. So the change of P1 is due to coming from state 2 minus leaving from state 1. I hope you can also see the connection with chemical kinetic that I was talking yesterday, right? So remember yesterday we discussed this reversible chemical reaction. A goes to B, B goes to A, right? And we said this is the rate. And it was exactly these two things. So in this case, concentration plays the role of probabilities. All right, so all of these are related. Good. Yes.
So in chemical reaction case, these rates were function of the dependent on the concentration, right?
No, okay, good question. No. So look, what plays the role of this rates U and W were rate constant. Okay, so there is important things. So the coefficient in front is called rate constant. The whole thing is a rate. But this is a rate constant. This is a rate constant. The rate constant is a rate per unit concentration. Okay. So, probabilities plays the role of concentrations. Probabilities plays the role of concentration. And if you wish, I can actually change this, make this equation like this one. So if I divide it by, let's say, A plus B, if I divide everything by A plus B, there will be probabilities here in chemical kinetics. So everything is related. Everything is the same things expressed differently, but it's the same thing. Now, if the system is more general, if there is a mini state, right, then you can easily generalize it, right? So the change of probability in this state I is due to all incoming fluxes from all possible other states, which are connected to the given one, minus all possible transitions out of this state. So the physical meaning of master equation is just a balance of probabilities. That's it. There is nothing else. Okay, so we discussed master equations as an important tool. There is another important concept that people use for understanding stochasticity and randomness. It's even called random walks. And as the best analogy, a drunk person, right? You can see there not so many drunk people in India, but still, if you go to countries like Russia, there are the minimal drunk people. Anyway, you probably saw drunk people. Yeah, so what they do is really random. Okay, so random walks concept is very useful in many areas. In chemistry, I can give many examples. Let me give you one example. So for example, you're looking at the material of the crystal, some crystal, and you are able to, with a laser, excite one of the atoms. So you're creating essentially so-called exciton. And this exciton in principle can diffuse, right? And the way what exciton is diffusing, it's a random walk. It goes all over. So it's a random walk, and people conveniently use this random walk in chemistry. It's not the only example. There are multiple examples, but it's one of the examples. Biology, also a lot of things here. For example, I found the paper which argues we use a random walk for understanding drug resistance. Random walk. So let's try to talk a little bit about random walks. I'm sure many of you know about random walk, but again, you can use simple arguments to understand things. The simplest things to do random walk, let's consider one-dimensional random walk. Okay, imagine there is a lattice of size, and suppose you with side I or state I, and the particle, random walker particle, can have a probability of jumping forward, probability P, the probability of stepping one step to the right, Q is the probability of stepping one step to the left. And in the simplest case, it's Q is 1 minus P. Let's assume that the time equals 0, you start in origin. It's arbitrary. Origin is arbitrary. Okay, good. So there is no time here. The simplest picture, only number of steps. Suppose I do n steps. So my random walker made n steps. I do random walk, right? So that's what I do like this. And suppose eventually I at the location at site n. I can also describe it differently. There is n r and some r step to the right and some l step to the left. So then you can have this relation. So this is the total number of steps, and r to the right and l to the left. And location is this one, right? It's because I started at the origin. Right? If it's not, then it will be additional additive constant here. Good. So it's convenient to look at the random walk dynamics. If I draw a scheme like this, imagine this is number of steps. Number of steps is essentially time, right? But let's say number of steps. I starting over there. This picture shows all possible trajectories if I make up to 3 steps total. If I make 3 steps total, I can go like this with the probability P, 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 or I can go like this, P, P, Q, or okay. All of these options are here, right? So the graphical picture is convenient. So what I needed to describe random walk. To describe random walk, I need to estimate this probability. This probability to find the random walker at the position M after capital N steps if it started at the origin. If I would know this probability, that's it. I would know everything about this dynamics. I can predict everything. So there are different trajectories, right? I already mentioned this trajectory. Over there, I showed you the different trajectories. So I can ask the question: what is the probability of trajectory which is right? Right, left. This trajectory is P, probability P to move to the right, Q to the left, so P squared. That's probability. But I can ask different question. What is the probability that I would make 2 steps? Sorry, questions? No. So what is the probability if I make 2 steps to the right or 1 step to the left? In any order, not necessarily things. And it will be different answer, right? It will be 3 P squared Q. You understand? 3 comes from, because there are 3 possible combinations. RRL, RLR, LRR. So let's come back there. I can go like this, I can go like this, I can go like this, right? So essentially, generally speaking, I can write an expression for the probability to find the random walker at position M after N steps, because this corresponds to this second probability. Yeah, and so it has P to the power N sub R, Q to the power N sub L, because we need NR steps to the right, NL step to the left, and then this is this binomial coefficient, right? Binomial coefficient reflects possible combinations. So that's how we derive it. And it's convenient frequently to the same scheme, but the numbers here shows how many pathway I need to reach this point. To reach this point, I need only one way. It's only one way to do it from here. To reach this point, also only one way to do it, and it's here. So there's only one pathway to reach this, only one trajectory. To reach this point, there are 2 trajectories like this, right? To reach this point, 1, 1, and eventually 3 here, 3 here. You can actually prove even binomial theorem from here, but there's no the graphical proof. Okay, good. So this is the general formula. This is the general formula which we derived right now very easily. So there is a probability to find random walker at the position M after capital N steps. But that's given by this. So in this expression, instead of N, R, and L, I use capital N and N, right? So capital N is the total number of steps, N is the position. And I plotted this. So I took N equal 10 steps, let's say 10 steps, the probability of 0.8, and that's what we can plot. And you can see the things here. So, as I mentioned, this is a central quantity for random walks. That's because you can calculate anything you want. For example, you want the question, what will be the average position? So in other words, if you do N steps in this specific set of parameters, what will be the average position you will end up? Clearly, you just have to sum M of all the probabilities, and that will be the answer, right? Very easy to understand. You can calculate any moment. So this, for example, this variance. You can calculate anything in principle. Yes.
On the previous slide, that formula was also for M negative, it'll also work, right?
No, M is on capital.
No, sorry, M.
M. Yeah.
Okay.
In principle, yes. That's right. Okay, so that's a good point. The good question is there are also negative M, but they are really indistinguishable from 0. You're right. That's a good point. So just for illustration purposes, I didn't, but it is. This is because P of 0.8, so you mostly move forward. Probability to be backward is very small. Okay, so but so far that was strictly speaking, no time, right? I had steps, number of steps. But this number of steps is correlated with time, and I can introduce the time here. So imagine that average step is taking place with average interval tau, then the time is n tau. That's your time t. Then you can really introduce this rates, transition rates. It's a probability to move forward divided by this over this time interval, or probability to go backward divided this. And then you can really calculate other properties, like velocity of the random walker, diffusion constant of the random walker, whatever. You can calculate the thing. So this is known as a continuous time random walk. So what I told you before was so-called discrete time random walk. Was only steps. More realistic description is a continuous time, and that you can describe the thing with a random walk. Okay, so then eventually you can write this continuous time master equation, and it's exactly the same what we said before. It's a conservation of probability, the same that we discussed some time ago. It's a probability to come from the side before, probability to come from the side after, minus limit. So in this language, each position of the random walk can be viewed as a different state. Again, very similar to chemical kinetics, very different to master equation that we discussed maybe 10 minutes ago. Okay, good. So let's try to, let's try to go to another important concept which can be used, frequently used, is the first passage process. I was showing this picture already, this graph, right? So to remind you, if cells can produce proteins called p53, and this is in response to stress. So the more stress, the more p53 produce, and then eventually, when this amount of p53 reaches some threshold, cell will die. Is known as apoptosis. So the whole event can be viewed as the first passage. So first passage event means for the first time, your system, essentially, number of p53 reaches this number, this is the end. Many processes in biology like this. There are many processes in biology, in chemistry too, and this very convenient concept. I just had another example from biology, which seems to be so this picture comes from some paper. Apparently, some people do experiments this way. They put some trackers on some animals, and they see when for the first time line will get. In this case, was a line or something, right? So see, and you can start and see when for the first time they will collide it. And this is the picture. The lion looking for this. There is a whole business so-called prey-predator dynamics, and essentially many people use this first passage concept to understand it. Okay, so first passage. Important things to understand that this first passage idea is complementary to master equation approach. It's a complementary. It's not a different one. It's the same. You can get the same results from both of these concepts. But let's try to look at the first passage processes. And again, you do the simplest possible picture. Imagine there is a lattice, but for convenience, let's say there is a lattice. This is the end of the lattice here, position 0. This is the left end. This is the right end. For example, if you think about in terms of motor proteins or molecular motors can eventually bind here. This is forward binding site, or molecular motor can bind here. This is the backward binding site. And for the first time when its molecular motor reaches this, this is the first passage you get. You can write equation very similar to master equation. In this case, it's known as the backward master equation. But let's try to kind of argue how to write this equation. So first of all, the most important things here is in the first passage, we're dealing with different probabilities. So to remind you, before we were dealing with the probabilities of finding particular given state at time t. First passage is dealing with different objects. Before reaching the side it's starting at position I at time equals 0. You ask me, what is the probability that you will reach this forward binding site for the first time at time t before reaching this? And this probability, you can describe it in this way. So again, very similar arguments that we had when we were deriving master equation. So what will happen after the time tau, average time of transition, right? With this probability, you will move to the state I plus 1, right? So then it means this will be this. Or with this probability, you move to the state I minus 1. Make sense? You understand, right? So before was different quantities, this is this probability. That's enough. And tau is this average time interval between the random walker jumping forward and backward. And from here, you can get this master equation again. You just expand it in terms of small, and you will get this equation. It looks very similar, but it's actually different. I will show you in a moment. So this is known as the continuous time backward master equation, which describes this quantity. Probability for the first time to reach position n at time t if you started at position I. That's why there are two indices here. Okay? In probabilities we discussed before was only one index, given state. Here I have to have two indices because I need to identify where I start. Okay, makes sense. For reasons I don't quite understand, this first passage pictures are very rarely explained anywhere. So there's like one or two books, but this is very simple things at the same level of the way we discussed it, and we will see. Okay, so essentially, when we think about first passage processes, it's convenient to use this Monte Carlo simulations thinking. Everybody knows how to do Monte Carlo, right? I guess, right? So the way to think, you don't have to do it, but it's easy to think this way. Imagine that you're starting at position I, and you do your Monte Carlo simulation by the rules I described, but then you stopped it, your Monte Carlo simulation, if you reach this position. So there are many trajectories. You will start here, many trajectories when you end it up before reaching this. So you have some unsuccessful trajectories that you ended up here. Garbage, not the garbage, you have to keep it. But you're looking at trajectories which will eventually end up here. And if you look in this space of these trajectories, then this first passage, this equation is essentially describes the probability of this trajectory. Okay. Yeah. So it's important to compare these two pictures. I said they are complementary to each other. They're complementary to each other. So before we had master equation, I just call it master equation, but correctly it's called forward master equation. Forward master equation. By the way, the language forward and backward comes from quantum mechanics, which is strange. That's because Schrödinger equation, in some sense, is the same as the equation for master equation written in a matrix form. So and there is a forward means the operator moves x forward and backward. So that's where language comes from. Okay. Good. So we're trying to compare forward master equation and backward master equation. Please look that you see that there is a here u p I minus 1, here u f n I plus 1. Do you understand, right? So in this forward master equation, the probability to be there is due to flux from this side plus this side, right? But here it's a different thing. Here the flux of those trajectories I was trying to explain is different one. Here in first passage language, the trajectories with rate u lie here. That's why it's I plus 1. Right? So it's different.
So here, if you're in continuous time, is this capital F, is it the density or?
It's a probability density per unit time. Yeah, I intentionally use different units so you would not be confused. It's still probability. It's a probability. Probability density is the right way to describe it. Yes. Okay. So that's what important things to understand. Forward and backward describe essentially the same phenomena, but differently. They're complementary to each other, and you can derive both of them reasonably simply. Just remember what is the definition. It's two different things. Okay. I argued that in biology, many of these phenomena are conveniently it is convenient to describe them using first passage because it's a first passage event. It's a threshold. So that's the reason people use it. Okay, so yeah, so it's convenient to plot this density so you will understand. So what I'm plotting here, this first passage probability densities. Again, so I took, okay, so I go back to the picture. I took n10, I took 10 sites, okay, and I is in my starting point, and I plot this first passage probability. And you can see if I'm at state 9, it's exponential. Why? That's because I'm sitting already over there. It's actually one step to reach the final binding site, right? This is 9, this is 10. That's what is shown over here. But if I'm starting in the middle, 5 somewhere, right? It's actually there are many trajectories before you can go there, so it's not exponential decay. So the function looks like this, and if it's I equal 1, it's even further away. Okay, and you can calculate important quantities. So in the forward master equations, we can say that we can calculate velocity, diffusion. You can calculate analogous quantities in first passage processes. The first quantity is the probability, known as the splitting probability. If you take integral of this probability density from 0 to infinity, it gives the probability that if you start there, that you will reach this side. Given the fact that there is another thing, it's not 1. If it's only one thing, the probability is always 1. But if it's another probability, it's not 1. And it's given by this expression. This is known as the splitting probability or overall probability of reaching site n. And there is another important quantity, which is the mean first passage time. It's essentially, the important things here is that you calculate it this way. The integral, it's not me. That's not me.
Yeah.
Update always comes at the right time.
So, forward technique for the probability distribution, the forward probability, that is also used to calculate the first passage time. Like
You can, but it's a little bit slightly more difficult. You can do it. So yeah, it's a good question. So let me explain it more. Yeah. So let me finish and I will explain. It's a good question. So this is a time. It's important that when calculating this time, you're dividing over the probability. And again, this Monte Carlo language is the right way to do it. Remember, I told you to think like Monte Carlo simulation, right? There is trajectory starting here, ending up here, but occasionally there are trajectories which end up here. If I look at all possible trajectories, splitting probability is the fraction of those successful trajectories over all possible trajectories. That's splitting probability. Right? Then when we calculate mean first passage time, it's so-called conditional time. It's a conditional on the condition that you are reaching the final state. And that's why you have to divide by it. So the question was, what is the relations that you can calculate mean first passage time also from forward? Yes, you can do it. And the way to do it is, so suppose I have again this system, and I can eventually calculate probability to be in any state. It's normal probability or stationary probability, essentially, right? Then I can calculate the flux to go to the final. So I calculate probability to be there times the rate. That will be the flux. Inverse of this flux will be mean first passage time. So remember, flux is number of particles per unit time. Inverse of this will be time between events going to the final thing. Okay, so you can do both. There are connection. Important things. Both these two approaches are equal. They're complementary. They're absolutely the same things. They're not. The only reason people try to use first passage that many of these biological phenomena, many experiments are done in such way that it's more convenient to look through the first passage lens. But it's absolutely the same thing. Okay, so that's my main message. Yeah, in principle, I don't want to move this is non-trivial topic. That's what I will probably try to stop. Feel free to ask me any questions, okay? So the important, so these are the main tools that people use for investigating stochasticity and randomness. So one is this master equation, and I explain you why, right? Because most of the phenomena on equilibrium, there is nothing else available, only this conservation of probability. Then this master equation, we can have forward master equation, backward master equation. It's the same things, but the quantities are different. Do not confuse probabilities. That's not the same probabilities. This probability is not the same as this probability. So pi here is not the same as this one. There's no there is a relation, but not trivial relation. And also we talked about random walk, all right? We talked about random walk, which is very commonly used in chemistry and biology. Again, random walk, but you can still get a lot of things from random walk, despite the fact that the walk is random. Some of the quantities are quite well defined, like mean, variance. You can still calculate things reasonably well. And the analogy, I can make analogy. So most people, I think, took thermodynamics, right? Classical thermodynamics. So in this room, there is a lot of molecules, right? A lot of molecules. Some of them move faster, some of them slower. But on average, there is one temperature here, more or less, right? Many molecules with different properties, but there are so many of the molecules, when you're averaging out, you're getting very narrow distribution, like delta function. That's the temperature. The same with the pressure. Many molecules, the pressure is essentially collisions with the wall, with the object. Different things here, but on average will be very narrow things here. So it's similar with random walk. It's random, but you can still calculate the average distance you travel. It's a specific number. Maybe I should go back again to random walk, because this is an important thing. Yes. So despite the fact that you are random every time, that every trajectory is random, you don't know. On average, after many trajectories, your average position will be given by this. If you repeat it many times, it will be deterministic, it will be known, okay? And the variance will be known, and whatever will be known. But every random trajectory you will see completely random. You don't know where it will go. But if you do many times, you will get your result. So it's very similar to what I explained to you, statistical mechanics. There is averaging of many fluctuating things essentially cancel each other, and you get a very almost deterministic things. So constant temperature, constant pressure, but this is just analogy. It's not exactly the same thing. Okay? Okay, good. So I would suggest I will stop here. Feel free to ask me any questions. This is non-trivial things. So the thing that you will not find in the textbook, this first passage thing, rarely you can find, unfortunately. For some reason, people do not, they think it's difficult. It's not. And at the same level, you can explain it as a form of master equation. Okay? And you can get a lot of things, and it's very convenient. Okay? Any questions?
So will it be possible for you to save the slides?
To share the slides? Sure. Again, I want to emphasize that I wanted to eliminate as much as possible mathematics. So I give you as simple as possible. So it's there is more mathematics. There is a couple excellent books on first passage things, on also master equation. But I give you, it's very simple things to explain. And as long as you remember what is each quantity is responsible, you can do things. Any questions?
You just mentioned there are a couple of books. Would you mind sharing the name?
Yes.
If it comes to mind.
Yeah. So essentially, in first passage, there is 3 books. The book number 1 is Nico van Kampen. It's a book. Nico. It's a famous book on Kampen. I think it's called Stochastic Processes. One chapter is devoted. The book has 20 chapters. One chapter is devoted. The book is called Stochastic. Stochastic Processes. I don't remember exactly. Yeah. nicely done. It's a little bit, on my taste, too mathematical sometimes. He was trying to define everything theorem and so prove it. Chemists and physicists like we don't really care of proving. So, but yeah, so this is book number 1. And then there is another book. Its name is Randomness. I think it's called First Passage Guide. First Passage. That's it. Guide. I have a book, and although it's not devoted to different one, but I have a chapter or essentially mathematical appendix which describes this whole my book on motor properties. Like, essentially, I use some of the things over there. So the book is motor properties. So it has a mathematical appendix, some discussions of first passage. Okay. First passage is also used. Finance people think that they can predict things in finance and so on. So, for example, crashes, stock market crashes. It's a first passage event in some sense, right? So it's a powerful tool. But I wanted to emphasize it's the same mathematical level complexity tool as normal master equations that we use. Any questions?
We can discuss formally.
Yeah. So I didn't want to put more into this because this is a non-trivial thing. So feel free to ask me if needed. Okay. Okay. If you want, you can ask one on one. A little bit too short. You can share with people.
Share it.